Welcome to The Explainer. Today we are diving into one of the biggest, most fundamental questions in all of science. What is the ultimate fate of our universe? A brand new, groundbreaking discovery is challenging pretty much everything we thought we knew, and it all starts with a map of the cosmos unlike any other.
So where is this all coming from? Well, it's from the largest 3D map of the cosmos ever created. And the data is hinting at something absolutely extraordinary, that the most dominant force in the entire universe, dark energy, might actually be running out of steam.
To really get your head around this, just think about it for a second. Everything we can see and touch, all the stars, the planets, you, me, everything, that's only about 5% of the universe. The other 95% is a complete mystery. About 27% of it is this stuff called dark matter, which is like the invisible scaffolding holding galaxies together. And a whopping 68% is dark energy, the mysterious force that's actively pushing everything apart. Now, for decades, the reigning champ of theories, what we call the LambdaCDM model, has worked beautifully. And it's built on one core idea, that dark energy is a cosmological constant. You can think of it as this steady, unrelenting background energy that never, ever changes. It just keeps pushing, making the universe expand faster and faster. This idea has been super successful, but that core assumption is now being tested like never before.
So the big question is, right, how on Earth can we possibly measure something from billions of years ago? Well, scientists use this incredibly ingenious tool, a kind of cosmic ruler that was left over from the very first moments of the universe.
This ruler is called Baryon Acoustic Oscillations, or BAO for short. The easiest way to think about it is to imagine a sound wave from the Big Bang just frozen in time. That's pretty much what it is. It's a specific, fixed-length pattern that got stamped onto the very fabric of the cosmos. And here's how it happened. Right after the Big Bang, the universe was this super hot, dense soup of particles. In the soup, sound waves rippled outwards from dense spots, kind of like dropping a pebble in a pond. Then, about 380,000 years later, the universe cooled down enough for atoms to form, and light was suddenly set free. That's the key moment, because it basically froze those sound waves right where they were, leaving a perfect spherical shell of matter at a very specific distance from its center.
And here is the magic trick. The radius of that frozen sound wave is always the same. It's a standard ruler with a length of about 150 megaparsecs, which is nearly 500 million light-years. Because we know its exact size, we can look for this pattern across the cosmos at different points in time. By seeing how big it appears, we can measure exactly how much the universe has expanded and how fast it was expanding way back then.
So to go out and actually measure these cosmic echoes on a scale that's never been done before, scientists had to build one of the most incredible instruments on the planet. Let me introduce you to the Dark Energy Spectroscopic Instrument, or DESI. Its mission, over 5 years, is to create this gigantic, high-fidelity 3D map of tens of millions of galaxies and quasars, all to precisely track the expansion history of the universe and hunt for clues about what the heck dark energy is really doing.
And the technology behind this thing is just mind-blowing. It uses 5,000 tiny robotic positioners. Each one is like a little fiber optic eye. They all move together in this incredible automated dance, pivoting to capture the light from 5,000 different galaxies all at once. It makes this survey unbelievably fast and efficient.
And the scale is just staggering. By the time it's finished, DESI will have mapped the positions of 40 million galaxies and quasars. Now, just to put that in perspective, that is more than 3 times what all previous surveys accomplished over the last 2 decades. And DESI, it's on track to do it in just 5 years.
By looking at objects that are so incredibly far away, DESI is essentially a time machine. It's mapping the universe as it was up to 11 billion years ago. This huge look-back time lets scientists track the influence of dark energy all the way across cosmic history. And this, my friends, brings us to the plot twist, because after analyzing just the first year of its data, DESI found something tantalizing, something that doesn't quite fit the picture we had.
Okay, so remember, the standard model says that dark energy strength is constant. Scientists represent this strength with the parameter called W, and it should always equal -1. Simple, right? Well, the DESI data hints that W isn't constant at all. In fact, it looks like it's been changing over billions of years.
And look, this isn't just speculation.
The DESI collaboration puts it right there in their own paper. They say, and I'm quoting here, that the standard model, LambdaCDM, is being challenged, and that a dynamical or evolving form of dark energy offers a possible solution to what they're seeing.
Now, the evidence gets even stronger when you combine DESI's measurements with other big cosmological data sets, like the cosmic microwave background or data from supernova. When you put it all together, the statistical significance of this deviation hits 3.9 sigma. Now, in particle physics, 5 sigma is the gold standard for calling something a discovery. But 3.9 sigma, that's way more than just a hint. It's really compelling evidence that something new might be going on.
So the crucial question is, how is it changing? Well, the analysis uses two parameters, W0, which is dark energy strength today, and WA, which tells us how that strength has changed over time. And what's wild is that the results consistently show WA as a negative number. This suggests dark energy was actually stronger in the past and has been getting weaker ever since, a scenario that cosmologists actually have a name for. They call it thawing.
And you might be thinking, okay, a few numbers are a bit off, who cares? Well, this is a huge deal. This isn't just some academic debate. The nature of dark energy literally dictates the ultimate fate of everything.
So let's be super clear about why this matters so much. First, it suggests our standard model of cosmology. One of the great pillars of modern science is incomplete, maybe even wrong. Second, it means we might need entirely new physics to explain what's happening. And third, it completely throws the endgame for our entire universe back into question.
For years, the leading theory was a future called the Big Freeze, where the universe just expands forever until it's cold, dark, and empty. That's what happens if dark energy is constant. But if it's weakening, like the DESI data suggests, it opens the door to a much more radical, dramatic alternative, the Big Crunch, where gravity could eventually win, halt the expansion, and pull the entire universe back in on itself.
And the crazy thing is, DESI is just getting started. There are years of data still to collect. But its very first results have already left us with this profound question to think about. If the most dominant force in our universe is changing right under our noses, what other secrets is the cosmos just waiting to reveal?